So, in the last lecture we discussed about fatigue and fracture. We said that though the construction of a material or the construction material used for manufacturing a machinery compared to that of an, let us say, construction of a marine structure may be steel, material is common, but still assessing the fatigue failure or understanding the fatigue damage or designing for a fatigue behavior will be different in both these cases, because though the material is similar in both the cases, but in the case of machinery you will know that the stress variation or fluctuations are in a specific state or in a specific range, and this is caused by the range of stresses applied on the material or on the machinery for a given design life, and one can easily estimate it by limiting the stress levels within the endurance limit. Whereas this concept cannot be applied to marine structures, because in marine structure there is a mixture of different kinds of stresses and fluctuations happening, and therefore one must estimate it in a different manner. Okay. Now, to design the marine structure against fatigue failure or fatigue damage, one estimates the fatigue life of marine structures. So, we estimate fatigue life. Usually the fatigue life estimates are done or made using SN curves. These curves are based on experiments conducted on different specimens. We can even say different types of specimens, to be very specific. How one can detect fatigue failure? How one can detect that the material or the member or the structure has failed by fatigue? Fatigue failure can be detected by three ways. Can detect fatigue failure by looking observation at three ways. When you notice an occurrence of a visible crack, when you notice a visible crack, or if you notice a through thickness crack, through thickness crack, or if you notice a complete loss of load carrying capacity, then you can infer that the material or the member or the structure has failed by fatigue. So, these are detections of a fatigue failure of a structural member. Now, let us talk about SN approach. SN approach. Steel specimens of various types are subjected to fluctuating loads usually tensile in nature. Number of cycles of failure, which I call as n, to the corresponding stress range the moment I say range, I am talking about the values of minimum to maximum. Okay, it is not a specific stress value, it is a range always, which is called as S, is plotted, which we call as SN curves. So, n seems to be proportional to some power of m. So, n is equal to some constant of where a and m are quantities derived experimentally. Suppose in marine structures, if we take measures to control corrosion, there are many techniques by which corrosion can be controlled. If I adopt all those measures to control corrosion in a marine structure, then it is seen that there is a cut-off stress below which fatigue failure will not occur. This is true even when the structure is subjected to cyclic loading. And that cut-off stress is related to two into 10 power 8 cycles. So, that cut-off stress corresponding to 2 10 power 8 cycles in SN curve is the threshold value. If you are able to employ some measures to control corrosion and the stress level is below this, which is corresponding to 2 10 power 8 cycles, then fatigue failure will not be initiated in marine structures. Okay? So, the stress level should be kept to that cutoff value, and that corresponds to 2 10 power 8 cycles in an SN curve. This is true only when measures to control corrosion are adopted. Without that, it is not correct. Okay? If you are able to do that, then this is the value. Now, in reality, for variable amplitude stresses and under the given environmental loading, this cutoff stress decreases as the fatigue crack grows. So, there will be reduction in this stress carrying capacity or the stress range capacity when they are subjected to real environmental loading and it is subjected to variable amplitude stresses. Interestingly, as m is the value which is indicative of fatigue life, the slope of the SN curve actually changes beyond 10 power 7 cycles from m to m plus 2. The slope changes. What does it mean is that the SN curve can be considered linear for preliminary analysis. Okay. It changes only beyond a specific number of cycles. Until then it remains a straight line. So, it can be considered as linear. If the designer is interested, look at the fatigue life, then the study of SN curve is significant in the range beyond 10 power 7 cycles. Now, let us look at in case of preliminary analysis. Where the slope of the SN curve remains constant. That is what we have said here. The SN curve is plotted as a straight line in a log scale. Slope of the curve is minus 1 by m, then the unity check for fatigue can be rewritten as u mth power design life damage where m is minus of slope inverse in this equation, if the slope is corrected to be as minus 1 by m. Okay. Now let us look more about SN curves before we plot one and show how they look like. SN curves are experimentally plotted. That is the first observation which we must know. The type of specimen which is used to plot is important, because this can also govern the slope of the SN curve. For example, if it is a welded structure, then M is 3. Now interestingly, the local stress effects caused by the weld or I should say by the shape of the weld on the specimen reduces the value of constant A. A is a constant, okay? We saw in this equation earlier. Next point is increase in thickness of the member also affects SN curve. It reduces the fatigue life. That is, it reduces A significantly, the value of A is a constant, and as we all know, fatigue life is decreased in free corrosion condition. Many international codes have focused SN curves to be very specific on tubular joints, because as you know, SN curves are influenced by the type of specimen and they are also influenced by the shape of the weld. So there are specific curves generated by conducting experiments on T joints or tubular joints. So there are SN curves that are generated for tubular joints very specifically. Especially for T joints. For example, one can look at what we call as UK T curves. A typical T curve or UK T curve looks like this. The log scale is also log scale, this is also a log scale. So let us say this value is 10 power 4, let us say this is 10 power 8, 5, 6, 7, 1, 10, 100, let us say 1000. It is a typical curve for T joints, it is a typical curve. The typical lesson curve. Plotted on a log scale, which is for T joints. Source UKT curves. So, we know that n is equal to a s power minus m, n also be a s power minus m for s greater than s dash, which is equal to infinity for s less than s dash. Let us see equation number 2. Alternatively, n can be also written as a1 s m1 or a2 m2 for s greater than s dash for s less than or equal to s dash. Where n dash s dash is the point of intersection of the two curves shown in equation 3. We can also write n dash can be a1 s dash minus m1, that is also equal to a2 s dash minus m2. For marine structures, a common equation which defines SN curve of A equals AC is used. Whereas the equation connects AC is given by where mu is the standard deviation, sorry, mean, and S is the standard deviation of parameter log n to the base 10. Typically mu is and S is 0.2, which gives me AC by mu A, is it not? Yeah, mu A, that is deviation of A is approximately 0. Further, we already know that A is influenced by the thickness of the material of the member. Therefore, A is also given by A reference T reference by T raised to the power of m by 4, equation number 6, where A reference is the reference parameter of the SN curve, T is the thickness of the plate which is being used for study, and T reference is thickness of the reference plate based on which SN curve is plotted. Both of them are measured in millimeters. Now, we already said that SN curves are experimentally generated or plotted on different types of specimen for a specific stress range. So, the stress range that is used to plot the SN curve experimentally is as below. R is the range which is stress min to stress max, which is greater than 0.5. That is the stress range which has been used generally to plot SN curves. This implies that the stress values are in the crack opening mode. Having understood that the stress strain, I would say the SN curves are plotted experimentally, shape of the specimen, type of the specimen, shape of the weld, thickness of the reference member all influence SN curve. Then let us quickly see what are the factors that affect use of SN curves, or the factors which makes the factors that make SN curves conservative, I mean safe. The foremost factor is relaxation of residual stresses. That is the first factor which makes the SN curve plotted as conservative plots. The second one is external stresses being partly compressive. See, whenever a crack is formed or propagated or initiated, let us say, if you apply further tensile stresses, there is a probability that the crack will get propagated or extended or expanded. Okay? When you apply a partially compressive stress to it, there is a possibility that the propagation of cracks will not be as fast as that of a tensile stress. In reality, if you see, there is always reversal of forces. So, the stress does not remain always tensile, it can also become compressive. Therefore, SN curves which are plotted based on stress ranges purely tensile will become conservative stresses. Okay? The third point, which is addressing the crack closure effects. There can be some parameters which can influence the closing of cracks also, which is completely ignored because the stress range which you are considering in SN curve plots are essentially on the crack opening modes. So, you are compulsorily causing a range of stress which results in opening of cracks, but in reality there can be a possibility that closure effects of cracks can be there, which we do not consider in the experimental manner of plotting the SN curves. Therefore, if you use SN curves to find out the fatigue life for a given stress range, how many number of cycles the structure can withstand, the values what you get from the conventional SN curve given in the codes will become a conservative estimate, and therefore, this conservative estimate is used for fatigue life assessment of marine structures. So, all these effects will result in lesser crack growth. Than that is projected by a conventional SN curve. So, all SN curves are generally considered to be conservative estimates. Now, there are some specific problems associated with SN curve. One advantage SN curve has is it is a conservative estimate. Okay, that is good. The other disadvantage what we have is SN curves are generally plotted for constant amplitudes. But in reality there is variable amplitude which is essentially caused by different environmental loads. So, that is a demerit. Now, how to handle this issue? Okay. Minus rule have been applied as a correction to the SN curve. That is the last topic what we will discuss today in this lecture. So, there is something called a minus rule which is applied as a correction factor to the estimate obtained from SN curves. So, this accounts for different amplitude stresses which a conventional SN curve does not. Therefore, for marine structures fatigue damage is preferably estimated using minus rule. Let us see what is this minus rule. If you are looking for fatigue damage of a joint, under n cycles of constant amplitude, amplitude loading, which could be n is equal to a s minus m, that is the estimate. We already know the SN curve estimate based on this equation, where m is the or minus 1 by m is the slope of the curve. So, the fatigue damage of a joint under n cycles of constant amplitude loading, which can be given by this equation for okay, let us put it as small n here. Is given by simply n by n. If the joint is subjected to variable loading, as the case of marine structures under environmental loads, then the load cycles should be divided into groups. These groups shall have approximately same stress range. If that is the case, if G such groups with same or almost equal stress range is identified, then in the given variable amplitude, let Sg be the stress range and Ng be the cycles of each group fatigue damage for each group is given by D of each group is simply Ng by Ng, where what is the equation number here? Where what is that? 8, where Ng is A Sg minus m, and call this equation number 9. So, you have got G such groups, each group you know the stress range Sg and the number of cycles for that stress range Ng. So, for each group the fatigue damage is simply with this number, but I want to find the fatigue damage of the whole structure or the member for subjected to variable amplitude. In that case, minus rule states that failure under variable amplitude load will occur when the following condition is satisfied. The condition is now interestingly the fatigue analysts refer the plot of Ng versus Sg as fatigue spectrum. So, in this lecture we have understood that how the fatigue assessment or the fatigue failure on marine structures can be estimated, why SN curves form a very major part in estimating the fatigue life of a marine structure, even though marine structure can be constructed with steel as a material which is similar to that of a machinery, where endurance limit is always considered as one of the criteria to find out the cutoff stresses, because here the main component is the stress variation range is very large and we are getting mixture of small and large amplitude load effects on the members, whereas in the other case in machinery this kind of variety of amplitude variation does not occur. So, SN curves play a very important role in estimating the fatigue life. So, the SN curves remains linear up to a specific number of cycles, which has been seen by experiments conducted on test specimens, and we have also seen what are the factors that influence the SN curve formation. And if a marine structure is controlled under corrosion or against corrosion, then one can say that the stress range corresponds to a specific number of cycles. If the stress range is not reached or not exceeded, let us say, then the fatigue damage will not be caused to the marine structure. However, when the variety of combination of loads and variation or variable in these loads occur or load effects occur on marine structures, the constants which form a part of the SN curve, which remains linear up to a specific value or 10 power 7 cycles, where the slope changes from m to m plus 2 as it has been seen in experiments, the constants a and m, the slope and the constant, get seriously affected by variety of parameters. Few important parameters could be thickness of the member or the material which you are assessing, another could be even the shape of the weld. Okay. Therefore, SN curves can be used only as a preliminary analysis of fatigue failure or fatigue damage, or essentially to estimate fatigue life. But in reality, in marine structures we have got composition or mixture of variables of load effects, whereas SN curves are plotted on a specific manner on type of specimen, where essentially the forces are remaining as tensile stresses. But here we have got other informations where the stresses can be compressive as well, and there is a mixture. So, the SN curve conventionally available, though they remain conservative, cannot be applicable to marine structures. Therefore, Minor's rule is a modification on SN curves which is applied for estimating fatigue life of marine structures. Marine's rules say that you group the stress range and the corresponding number of cycles of each group separately from a given stress history or stress range time history, and for each group you estimate the fatigue damage by this equation. If you really wanted to know what is the fatigue damage of the entire structure which is having different group of such groups, then you have to fulfill this condition. If this comes to around 1 or closer to 1, it is sure that the groups of these stress ranges will result in fatigue damage of the member. Okay. In the next lecture we will talk about the fatigue assessment on time history scale as well as frequency response in the next lecture. That will be our focus on the following lecture. Do you have any questions here in this lecture?
It was said that the experiments cannot match with the real time, but here SN curves are generated from the experiment.
Yes. You mean to say why it is so? I repeat again the same explanation what I gave. As you correctly said, yes, the experiments conducted on the lab scale to estimate fatigue damage cannot map exactly the behavior and the environmental loads on real time structures, agreed. But SN curves are done under controlled environment experimentally on various types of specimen only to estimate the preliminary damage or the preliminary fatigue life of a given member. So, only to estimate the preliminary fatigue life one can use SN curves as a design phenomenon. Okay. If you really wanted to look at the fatigue estimate on the design prediction of the structure under cyclic loading, one should look for the nonlinear component of the variation of slope components in SN curves, where the SN curve does not remain on the same slope or will not acquire the same slope. So, in the lab scale the experiments conducted to estimate SN curves cannot directly map the behavior in reality, but still to a greater agreement international courts do recommend fatigue life estimates based on SN curves. Okay, thank you.